Thermal vibrations of the atoms in a solid. Consider nitrogen gas in equilibrium within a box at room temperature. In accordance with the result of problem 1.9, it is then reasonable to assume that the average kinetic energy of a gas molecule is roughly equal to the average kinetic energy of an atom in the solid wall of the container. Each atom in such a solid is localized near a fixed site. It is, however, free to oscillate about this site and should, to good approximation, perform simple harmonic motion about this position. Its potential energy is then, on the average, equal to its kinetic energy. Suppose that the walls consist of copper, which has a density of 8.9 grams per centimeter cube, atomic weight of 63.5 grams per mole. Estimate the average speed with which a copper atom vibrates about its equilibrium position. So the question is V bar copper atom. Estimate roughly the mean spacing between the copper atoms in the solid. You may assume them to be located at the corners of a regular cubic lattice. So we're going to assume a cubic lattice. We're going to find the mean spacing between the copper atoms, so that's the lattice constant A. So that's basically what we will estimate. And when a force F is applied to a copper bar of cross-sectional area A and length L, the increase in length of the bar is given by the relation force per area, that is stress. This is basically called sigma stress, is Young's modulus times strain. So epsilon is called strain. Elastic properties of materials, where the proportionality constant Y is called Young's modulus. Its measured value for copper is 1.28 10 to 12 dynes per centimeter square. Use this information to estimate the restoring force acting on a copper atom which is displaced by some small amount x from its equilibrium position in the solid. So the restoring force is given by Hooke's law. The restoring force is equal to minus kx, as you know. And what is the potential energy of an atom when it is displaced by an amount x from its equilibrium position? For simple harmonic motion, it is 1 over 2 kx squared. Use this result to estimate the average magnitude of the amplitude of the vibration of a copper atom about its equilibrium position. Compare x with the separation between the copper atoms in the solid. Okay, so we're going to estimate x, and we will find x to lattice constant ratio. We will compare these two. Okay, so that's the problem. Now we have, let's list the given quantities here. We have a copper container. The density of copper is 8.9 grams per centimeter cube. The atomic weight of copper is 63.5 grams per mole, and this is going to be in equilibrium, thermal equilibrium with the nitrogen gas. And in the problem statement, it is stated that also, as we found out from problem 1.9, mean energy per atom of the nitrogen molecules, mean energy per molecule will be equal to the mean energy per atom in the copper. So for nitrogen, we will have 1 over 2, assuming that we have only kinetic energy, V nitrogen square bar, this must be equal to 1 over 2 mass of a copper atom V copper square bar. So we will see that if we estimate V copper bar square to be almost the same thing as V copper square bar, we can estimate the mean speed of a copper atom as the mean speed of a nitrogen molecule times, because the 1 over 2's cancel, square root of mass of the nitrogen at the molecule divided by mass of copper. So that means this is going to be mean speed of copper is first I need to remember the mean speed of a nitrogen molecule. Now again we're using the values that were calculated in the book. So if we go back to previous problems where we have used this quantity, for example in, let's see, problem 1.8, where we have taken this V bar 5.1 10 to 4 centimeters per second, which was for nitrogen gas at room temperature, atmospheric pressure in a 1 liter container. So let's take this value to estimate. So we're going to use this value 5.1 times 10 to 4 centimeters per second. This is at room temperature, 1 atmosphere pressure in a 1 liter container. So this is where we got these numbers from. So that's what we calculated before. So this is going to be then V bar copper is 5.1 times 10 to 4 square root mass of a nitrogen molecule is, so I have to remember molecular mass of nitrogen, it is 28 grams per mole. It is 28 divided by Avogadro's number divided by 63.5 divided by Avogadro's number, so Avogadro's numbers will cancel. So basically this will give me the end result. So from here I can calculate the mean speed of a copper atom to be 3.4 times 10 to 4 centimeters per second. So this is going to be our estimation. Now in part B, we're assuming that these copper atoms are forming a simple cubic lattice. So let's draw a simple cubic lattice here. They're sitting at the corners of this simple cubic structure. So we can place our copper atoms here at the corners. And there is 1/8 of each atom inside the cube. So each corner will give us 1/8 of an atom inside the cube, and we have 8 corners. So 1 over 8 times 8, 1 atom per cube. So in 1 cube we're going to have 1 atom. And the spacing between the atoms I call A, the lattice constant. Okay. So I'm going to, the problem was to estimate the mean spacing, the lattice constant. So basically I can say that the density of copper is mass of one copper atom divided by the volume it occupies, and the volume it occupies will be a cube here, because I see that there is one atom per cube, so I can estimate A to be mass of copper divided by density of copper to the power 1 over 3. So if I substitute these values here, the mass of copper is 63.5 grams divided by Avogadro's number 6.02 10 to 23, that's mass of one copper atom, and density of copper is 8.9, this to the power 1 over 3. I can find that A should be 2.3 times 10 to minus 8 centimeters. Okay, let's move on to part C of the problem. Now in part C, when a force is applied to a copper bar, we have stress is equal to elastic modulus times strain, and this Young's modulus value is given in CGS units here. So Young's modulus is 1.28 times 10 to 12 dynes per centimeter square, and the force per area is Young's modulus times delta L over L. When we apply a force per area on one side, we see that the area that we will apply the force to for 1 cube will be A squared, and here we will have Young's modulus times delta L over A. So we're going to see that the force will be given by Young's modulus divided by the lattice constant A times delta L. Now this is in the form F is equal to Kx, the restoring force. So we can basically say that our spring constant K is so here is not divided by A, it's multiplied by A. So this is Young's modulus times A. So Young's modulus times A will be the spring constant. So this will be 1.28 times 10 to 12 dynes per centimeter square multiplied with 2.3 10 to minus 8 centimeters, which is our lattice constant A here. So this will give us for K 2.9 times 10 to 4 dynes per centimeter. Therefore the force will be Kx 2.9 times 10 to 4 x in dynes, if x is in centimeters. So this will be the restoring force that will be appearing on a copper atom. Okay, so let's move on to part D. In part D, we're talking about the potential energy of the simple harmonic oscillator. The potential energy we can calculate to be for a simple harmonic oscillator, it is 1 over 2 kx squared, and its average value will be equal to the average kinetic energy, 1 over 2 mass of copper V copper square bar. Again, 1 over 2's will cancel, and we will see that 2.9 times 10 to 4 x square bar will be equal to mass of copper 63.5 grams per mole divided by Avogadro's number 6.02 10 to 23, and 3.4 10 to 4 centimeters per second is what we found in part A squared. So this gives us, for with the approximation x square bar is x bar squared, for x bar we will calculate a value of 2 times 10 to minus 9 centimeters. So that basically gives us the end result. And if we want to compare x bar with the lattice constant, x bar divided by a, now x bar we found to be 2 times 10 to minus 9 centimeters. The lattice constant a we found to be 2.3 10 to minus 8 centimeters. So we see that this roughly corresponds to 10%, roughly 10% of the lattice spacing. So this is the amplitude of the oscillation of vibration of the copper atoms about the lattice sites. The amplitude is about 10% of the lattice constant A. Okay, so let's review what we said. We're talking about nitrogen gas in equilibrium inside a container at room temperature. It's in equilibrium with copper. The average kinetic energy of a gas molecule is roughly equal to the average kinetic energy of an atom in the solid wall of the container, and the atoms in the container are free to oscillate about their peak lattice sites, and they will perform simple harmonic motion so that on average their potential energy is equal to the kinetic energy. And the values for copper are given, density and atomic weight. We want to know mean speed of a copper atom. We want to know the lattice constant, assuming that we have a regular cubic lattice. We want to know the restoring force a copper atom would feel when it is displaced from its equilibrium position by a small amount x, given that Young's modulus is listed. And we also want to know the amplitude of the oscillations and compare it with the lattice spacing. Okay, so this x that we're talking about here is the amplitude of the simple harmonic oscillator. Now, since the mean energy per atom for nitrogen and copper should be the same, the mean kinetic energy, we have basically this approximation: V bar copper is V bar nitrogen, square root of mass of nitrogen divided by mass of copper, and that gives us 3.4 10 to 4 centimeters per second. We have used the value of V bar nitrogen from a previous problem, and also it was given in the text. For room temperature, 1 atmosphere pressure inside a 1 liter container, it was 5.1 10 to 4 centimeters per second. Now we're assuming that these copper atoms are perfect spheres centered around lattice sites here. So I wasn't too successful in drawing perfect spheres centered around lattice sites here. Okay. So for each one, we have 1/8 of the sphere is contained within a single cube. So basically you have to consider the other cubes that are neighboring this one in order to see this. So you can see that you will have um, 1/4 of it in one plane. So you have this is number 1, number 2, number 3, number 4. So it's shared by 4 squares here, and half of it is up, half of it is down. So you get 1/8 of a sphere that is contained within a cube, and 8 corners. So that gives us 1 atom per cube. And density of copper is mass of copper atom divided by volume occupied by one copper atom. So that gives us a lattice spacing 2.3 10 to minus 8 centimeters. Then we have used the stress-strain relationship, force per area, force per one side of the lattice, a square, is Young's modulus times delta L, or delta A if you wish, divided by A. So Young's modulus times A times the amount of deformation delta L gives us the force. So that is in the form F equals kx, the restoring force formula. So K is Young's modulus times A. So we find that in CGS units this would be 2.910 to 4x in dynes. And the potential energy mean value is equal to the kinetic energy mean value for a simple harmonic oscillator. So using this relationship and substituting the values we have obtained previously, we have for the amplitude of the oscillations 2 10 to minus 9 centimeters. It's about 10% of the lattice spacing that is the amplitude of the oscillations. Now about the units here, the only thing you may not be familiar with is dynes. So if you wish to compare this to newtons, 1 newton is 10 to 5 dynes. So you can basically convert this to newtons if you wish to SI units by using this conversion.